We talk about the use of redundant links, for instance, in a topology, a meshed topology like this one. This is a typical partially meshed network. This kind of topology permits that if some link fail, the network could forward the frames over other links that are redundant links. But the use of this kind of topology, when we use bridging or switching techniques, methodologies of forwarding in those devices, will produce what we call loops. The loops are produced because when, for instance, this device sends a broadcast over, for instance, this segment, this collision, this collision domain, the broadcast is received by this switch. Switch forward the frame over this segment, for instance, and over this segment. The frame that is forwarded over this segment is received by this switch, and this switch then will forward this broadcast frame over this other segment. Then now this bridge or switch will receive and forward again the same broadcast frame over this segment, and in that way a loop happens. A loop will happen in this part of the topology, another loop in this one, another loop in this one. And the loop generates traffic that is unsupportable. That is, the switches will crash if a loop happens in the network. And then it's important to avoid to open the loops. In order to open the loops, we need to block some ports. For instance, if we block this port, for instance, this loop will not happen, this loop will not happen. We block this port, this loop will not happen, and in that way, when we block some ports, we transform fully or partially meshed topology in a tree. A tree is a topology without loops. In order to block some ports and in that way transform any topology in a tree topology, we could use what we call the spanning tree protocol. The IEEE proposed different solutions of spanning tree. The first one was 802.1d, the original spanning tree protocol. After that, proposed the .1w that is called rapid spanning tree, or for instance the .1s called the multiple spanning tree protocol that permits typically more than one tree possible, for instance for different VLANs. And for instance, this is a well-known protocol, .1q, that include those specifications. And finally, this is one of the last standards that propose a particular spanning tree algorithm in some scenarios. In order to implement that spanning tree protocol, remember that we would like to exchange some particular messages between the switches in order to know in some way the topology, and finally in order to transform this topology into a tree, avoiding the loops, the possible loops. Then what the switches perform is the exchange of what is called BPDUs, that is bridge protocol data units, used by the spanning tree protocol. Then typically the BPDU is encapsulated to an LLC frame and transmitted over the Ethernet network. Pay attention, there are different fields that are coded in for instance, protocol ID, protocol version ID, type, flags, route ID, route path cost, bridge ID, port ID, message age, max age, hello time, forward delay. It's a relatively complex protocol, but what you need to understand is the basic concept. The basic concept is that the spanning tree protocol, the protocol exchange by the switches, not by the end systems, not by the stations, but only by the bridges and switches that perform LAN switching in LAN switching network. And the main goal of the spanning tree is finally block some ports in order to avoid the loops. Then, for instance, there are typically some definitions that you need to know. For instance, every switch network will have a bridge ID. The bridge ID is a number that identifies the switch within this broadcast domain. And then typically, for instance, the bridge with the lower bridge ID will be recognized by all the switches as the root bridge. The port or link cost, in fact, is the cost, is a metric that represents the cost to pass traffic, to pass a frame across a particular port or link. This port or link cost permit the calculation of the path cost to the root bridge. For instance, thanks to the exchange, the BPDU exchange, for instance, this switch will know that he could reach the root bridge with a particular port or link cost. When this switch propagates this information to the other switches, now that switch here will know now, we learn that he could reach the root bridge with the cost, path cost, the root bridge equivalent to the port or link, this link cost plus this other link cost. That way, then the switches could compare if they could reach the root bridge by different paths. The switch could calculate which is the best port in order to reach the root bridge. For instance, if we suppose that each link has a cost of 1, for instance, the cost to path cost to the root bridge from this switch will be 1 across this port and 2 across this other port, and even 1, 2, 3, 4 across this port. Then the switch decide that having 3 ports, only this is the best port in order to reach the root bridge. Then this is called the root port in the switch. Every switch different from the root bridge will have one and only one root port. Another definition is the designated port. For instance, in this segment, there are 2 switches competing. Each of those switches send a BPDU over this segment. The BPDU will be compared, and only one port with the segment with a collision domain segment will be the designated port. Then, in that case, only the one of those will be the designated port. In this case, excuse me, but is in a collision domain, not a broadcast domain, the designated port. And that case, for instance, the designated port will be this one. Why? Because the comparison of the BPDUs is performed using first, which is the root bridge recognized by the switch. Second, which is the path cost to the root bridge. And after that, which is the port, the bridge ID, and the port cost indicated in the BPD. In fact, we have the root ID, the root path cost, and the bridge ID and the port ID in order to compare and decide which is the designated port in a collision domain, in a particular collision domain. And then, for instance, if the 2 BPDUs have the same root ID, the designated is determined by the lower root path cost. If the 2 BPDUs have the same root ID and the same root path cost, the designated port in the collision domain will be designated based in the lower bridge ID. And if the root ID, root path cost, and bridge ID of the BPDUs are exactly the same, the designated port, in fact, will be the port that is sending BPDUs with the lower port ID. In that way, the designated port is determined, and finally, for instance, in any switch, the ports that are not a root port or the ports that are not designated ports in the collision domain are blocked. Then, for instance, in this case, this switch determines that this is the root port, that is the port that permits to reach the root bridge with the lower path cost to the root bridge. And in this collision domain, this was the designated port, but in this collision domain, this wasn't the designated port. Why? Because, in fact, for instance, in this segment, this port send, for instance, BPDU that say that the root bridge is 3, and the root cost is 1, and the root bridge is 24, and this is better than the BPDU sent by this port that say that the root bridge is this one, the root cost is 1, but the bridge ID is 92. That's why the designated port in this collision domain is this one and not this one. And that's why this port is not a root port nor a designated port. Then there is a port that has to be blocked by the switch. In that way, the spanning tree will transform any topology in a tree topology, avoiding loops. The spanning tree is quite complex in order to function. In fact, the spanning tree involves different states. That is a protocol machine or yes, or a state machine that evolve different across different states. For instance, typically the forwarding state, in fact, this machine is applied to each port. Then, for instance, all those ports are in the finally in the forwarding state, and for instance, those ports are in the disabled or blocking state. But for instance, we could see that if a failure occur, for instance, here, see what happened if a failure occur in this segment. The failure occurred in this segment, what will happen is that in fact this was a designated port, but after that, and this is, was a root port, but in fact what will happen is that that case the root port will change from this one to this one, and then what will happen is that the bridge PDU sent by this switch over this port will be compared with the BPDU that this switch could send across this port. And in that case, what will happen is that this switch decide to change the state of this port. This port was in the blocking state, and but in that case, in this collision domain, a change will be detected because this switch start to send BPDUs with root bridge 3, but with a higher root cost compared with the root cost of this switch. And that's why this port will be pass from the blocking state to the this port pass from non-designated port to designated port, and then from will pass from the blocking state to the forwarding state.